On the far edge of the solar system, the most distant man-made object, the Voyager 1 space probe, is flying away from the Sun at an astounding 17 kilometres every second. That's 38,000 miles per hour. It didn't just get there on its own steam, it didn't just get there on its own burners, but it got there using an interesting principle called the gravitational slingshot. And the gravitational slingshot is what happens when the probe flies past another planet and picks up some of the momentum from that planet. And you can understand the principles of this using simple A-level mechanics. And we're going to demonstrate that to you today using just these two little rubber balls. To understand the gravitational slingshot effect, you've got to imagine that one of these objects is very much bigger than the other one, so that upon the collision, the speed of the larger object is barely affected at all by the collision. It might lose a little bit of momentum, but not very much at all. And so, for example, if this was a train moving at a certain speed, let's call it u, and this is a small ball hitting that train with a speed v, then after the collision, the train is still moving more or less with a speed u, but this little object flies off the train with a speed equal to its initial speed v plus twice the speed u of the train. So it can pick up an awful lot of velocity that way. In the same way, if this is a planet and this is the Voyager spacecraft flying past the planet, there's no actual collision because they interact only through gravity, but the same principle applies. You can still think of this as being an elastic collision. And so the Voyager spacecraft gets its initial speed plus some of the speed from the planet. It's not a direct head-on collision, so it doesn't get the full speed of the planet, but it picks up some of the momentum from the planet and gets thrown off into the far reaches of space. To illustrate the slingshot effect, what we're going to do is find out what happens when you drop these two balls with a small ball on top of the big ball. But before we come to that, let's just think about what happens if you just drop one ball on its own. It converts its initial potential energy into kinetic energy, so it reaches the ground with a speed u, and then it bounces back up again if it's an elastic collision with the same speed u, and should in principle reach its initial height. And this one almost does that, but not quite. So what happens then if you've got one ball on top of the other? Let's imagine they're just slightly separated. So they both travel down and reach the ground with the same speed u, but the big ball at the bottom bounces first and then starts moving upwards with the same speed u. And this small ball is still travelling downwards with the speed u. So they meet in such a way that their relative speed, the speed of the big ball minus the speed of the small ball, is twice u. But because this ball is so much bigger than this small ball, the collision doesn't really affect the speed of this big ball. And so they separate again so that their relative speed is 2u. The big ball is still moving upwards with speed u, so the small ball must start moving upwards with speed 3 times u. And because it's now moving upwards with a speed 3 times u, it then transfers all its kinetic energy back into potential energy. So in principle, this small ball should be able to reach a height of 9 times the original height from which it was dropped. Now, of course, the collisions aren't perfectly elastic, and this ball is not that much bigger than this ball, so you'll never quite get 9 times the original height. Also, it's very, very difficult to line them up perfectly. But we can see what happens when we drop the small ball on top of the big ball. So the same principle that can be used to send Voyager spacecraft to the edge of the solar system can be used to launch small balls a little bit higher in the air than where you drop them from. So understanding the principles of spaceflight and this gravitational slingshot effect is just one simple application of mathematics out there in the world. But mathematics is the language of science. and it gets used in a whole host of different areas of science and technology, from designing aircrafts through to understanding how chemical reactions work and through principles of quantum mechanics, through to understanding how to combat cancer by modelling tumour growth and working out how nutrients flow into tumours, through to understanding how the genetic code works and understanding which parts of that affect different areas of life. So there are many challenges out there, and mathematics is a great tool for dealing with all of those.